okay? I was going to ask Jason to give the lectures, but he said he's not here. So no class the week after Thanksgiving, okay? So, and I will do a review lecture the Tuesday, December 4th, I believe.
December 4th.
Right, still, I think there's still class on 4th.
Yeah.
All right, so we will be back on the 4th. So don't eat enough turkey because you have to work on the homework. Okay, is the light on?
It's on.
All right, the light is on. So even though I have moved these topics of unsupervised learning to the course in the spring, which is basically machine learning 2, I thought for diversity of concepts to at least so you can see something to discuss a little bit of model reduction in a very elementary way in the context of what's called the principal component analysis. I can tell you that it doesn't matter what you do. If you don't know what PCA is, it's not good. Okay, because PCA comes with 50 different names in sciences, and lots of people have made career on this, changing the names and reusing the same techniques. But one way or another, this is the most basic, the most elementary technique used for model reduction of high-dimensional data. All right. So let me, again, we're going to try to avoid lots of details today so we have an easy lecture. So let's say that somebody gives you data that consists of the handwritten digit 3. Okay, so this is sort of a pixelized image. And you can think that these digits are basically 64 by 64 pixels, but you really do some padding, you put all these blank pixels around, so it is, the dimensionality is 100 by 100. So what I'm going to do is I'm going to take this image 3 and take the 3 and translate it, rotate it, etc. And I'm going to ask you, if I create lots of versions of this image 3 by translation and rotation, I'm going to be getting something that looks like this. Okay? So this is the same image, and I have done different ridge body motions. So if I give you a huge data set consisting of this digit 3 that vary by rotation and translation, and I ask you, what is the intrinsic dimensionality of this data set? Some of you will go and say it's 10,000. All right? Some will say, no, it's only 3. Because all of these data sets really, they differ by horizontal, vertical displacement, and rotation. All right? So this, of course, a very easy case. And, you can guess that the intrinsic dimensionality is 3. But what we would like to do is, we would like to have some formal method where if somebody throws you data that you cannot even visualize the way that you do here with the digit 3, figure out what is the intrinsic dimensionality, what's the low dimensional manifold for these data lots. By the way, in the context of the letter 3, don't get the impression that this is an easy problem, because I only did translation and rotation, but I can do deformation to the digit 3, right? I can take it and deform it. And if you sort of start doing nonlinear mappings, the situation becomes a little bit more complicated. Okay, so more complicated, and this manifold that we're looking after is nonlinear, because if you take this digit and let's say you move it by 1 pixel, this pixel from a blue pixel becomes a white pixel, right? So the mapping is highly nonlinear. And so we will need some means to understand how to deal with that. All right. By the way, these ideas of trying to remove rigid body motions and rotations from data, it sounds a trivial thing. It is not actually very trivial, and most people in the literature, they don't bother to do it, which means they get results that actually they're not correct. So this is a very important topic of research as we speak. It's like, how do you figure out any rigid body motions in your data so you can go and remove them, right? So you can think if this, for example, instead of images of 3, there may, let's say, molecular arrangements in high-dimensional space, I can take the atoms, move them, rotate them, etc. How will you be able to actually make sense unless you remove those the rich body motions out? So it is a significant problem. All right, so what I'm going to do is I'm going to start actually describing the problem in the difficult way, and then I'm going to become elementary, and then I'm going to come back to the mathematics on this generative point of view. So first, what does a generative point of view means, right? When you do, you try to identify the low-dimensional manifold. It's like doing model reduction, but really the way that I would like you to see the problem is as a problem of using this low-dimensional manifold as a generator of the high-dimensional data. Okay, so somehow, if you learn the low-dimensional manifold, you're going to build a mapping from, let's say, from 3 dimensions to 10,000 dimensions where that digit 3 was lying. So that view is called generative point of view. Generative means, it will allow you to generate more data similar to the ones that I gave you. So what's the idea mathematically? It's very simple. We're going to introduce some latent variable z with some distribution p of z. So you can think of z being the low-dimensional representation of your data. And then you're going to build a mapping from z to x, all right? So from low dimensions, you're going to go to high dimensions, okay? So we're not simply going to see this as identifying what z is, but we're going to look at this problem as a generator of the high-dimensional x from the latent representation z, okay? This is very much different from the way that you think of model reduction. Everybody says, oh, reduce the data in 2 dimensions or 3 dimensions so you can plot them. No, here really I want to reduce them not because I'm going to do modeling in z, but because I'm going to build a mapping from z to x. And you may wonder, how can you do this? Because z is low dimensions. How can you go from low dimensions to high? Well, probabilistically, everything is possible. Okay? And all the activities now in generative models in deep learning, they're around this idea. So this is very powerful, but we're not going to do any of that today. So let me give you some examples of how this is going to work. Let's say you are going to select some latent variable z, and I make them here in an isotropic Gaussian. And then the mapping from z to x is going to look like another Gaussian, where the mean is w times z plus mu, and the variance here I'm using an isotropic variance. Okay? Now, z is going to be lower dimensional than x, which means w is not going to be a square matrix. Right? So w is going to be lots of rows, a few columns to account for the fact, okay, that z is a reduced representation of x. So the idea here is that somehow, if you sample z through this mapping, you actually generate realizations of x. And like in our case with the digit 3, you may say, well, how is this going to fall in place? Well, since I give you lots of data, you're going to use the data to compute what w is and to compute what sigma square is, so that this model makes sense. And the way we're going to compute them, the most trivial way is to actually maximize the evidence of the data, which is basically p of x. And we will do that calculation later on in the lecture today. So what actually you see, literally these 2 equations, falls under the category of what we call probabilistic principal component analysis. And as I said, I'm going to come back to discuss this in more details, but I'm going to show you a graphic, and then I'm going to go many, many steps backwards to do non-probabilistic PCA and then return back to this, okay? But for now, you can think z is the latent representation of the high dimensional x, and you build a probabilistic model from z to x through this Gaussian, and the main thing basically to be able to make sense out of this would be to calculate what w is and what sigma square is and what this whole thing looks like. So let me, I'm going to give you a picture, and this picture is going to come back later in the slides. if you understand this picture, you really understand how these generative models work like. So let's say we took P of Z to be, let's say Z, we take it to be one-dimensional, and X to be two-dimensional. So really, we do model reduction from 2 dimensions to 1 dimension. So according to our model, right, we're going to select a Z from this isotropic Gaussian. And then if you remember, the probabilistic model would be a mapping from Z to X, which is of this form. And if you look carefully, basically what I do is, I consider W basically here is going to be a vector in 2 dimensions. All right? So the mean of X will be mu plus W times Z, all right? So basically this will bring me to, let's say, this point, plus some noise that I put around that point, okay? So effectively, you're able to go from 1D to a point in 2 dimensions, okay? So we can do this probabilistically, and we do this sort of with a linear method because the mapping that I use here, you notice, is linear in Z. Okay? Now all of this assuming that, again, we can compute what W is and we can compute what sigma squared is. Now, so let me go back to these 2 equations. If I give you P of Z and I give you P of X given Z, you can actually integrate Z out, and if you integrate Z out, you actually get, this distribution that you see here, all right? You actually get a likelihood, if you like, all right, that is a Gaussian with a mean mu, and a variance sigma square I, that's the noise, plus W times W transpose. I'm gonna show you these equations again, but this is nothing else but basically integrating Z out, and I give you a very general equation here, but if you integrate Z out, you multiply this by that, and you integrate in Z, you basically get something like that, so you get a Gaussian like that, okay? So the idea here is, this Gaussian that you see here is in 2 dimensions, all right? But our model actually is able to generate realizations of little x by sampling in 1D. All right, that's the idea here, okay? So effectively, we have identified Z to be the latent representation of X, and Z is capable through this mapping to actually give me realizations of X. I'm gonna, maybe, let me just say this now, in case we don't have time later. You can actually generalize this type of models. So instead of having an isotropic Gaussian, you can put any mean and covariance you like. And you can generalize this mapping by, instead of having an isotropic noise level, you can put anything you want there. And different forms of this come with different names. So if you have seen this in the literature, if you see factor analysis, you know, that's the model basically, okay? And actually, in the particular case where this matrix psi is diagonal. So there's a lot of versions of this type of things. Actually, if you search on the web, you will find whole books like that, only on principal component analysis, which means in principle, we could have a whole course on principal component analysis, and all of you enthusiastically will take it, okay? It's a very fundamental topic everywhere, right? In imaging, in data compression, in engineering, in everywhere, in signal processing, everywhere. All right. So I'm going to do a very, this example actually comes from Murphy's book, but it reminds me actually a PhD thesis of a student somewhere in Germany that I was in the committee, because he was literally doing this type of PCA modeling that I thought really has no value, but it had values for the auto industry in Germany. So here's what the idea is. We're looking at the data set that has dimensionality 11. So you know you have 11 variables, right? So your little x that I was talking before has 11 variables. We had so many data points, 387. And the variables, these 11 variables, are things like engine size, number of cylinders, miles per gallon, etc. Okay? And the idea was to be able to visualize and know what's going on. They want, to be able to plot this data in 2 dimensions. All right? So what they will do is they will use these realizations and do some analysis, which is principal component analysis that we discussed today. They will plot them in, they will project them in 2 dimensions. And in addition to projecting the data, what actually they will do is they project the future dimensions 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1. Okay? So basically they will take, if you imagine that you have something like in 11 variables, they will project each of these directions also in 2 dimensions. Okay? So what comes out is a plot that looks like that and can be very misleading. And again, the details are unimportant. But this particular plot, right, says, look, all of these are basically these future directions, okay? And the vertical axis actually corresponds to the variables that, I mean, when you plot this, you will see that it corresponds to fuel efficiency, because the cars that they are, you know, inefficient in fuel, the more inefficient they are, the more up they are on this axis, okay? I mean, I can see here it says, what is that? Kia Sorento, I suppose that's a little tiny car, right? And I don't know what those cars, GMC something, you know, an animal, you know, okay? And similarly, the horizontal axis, it comes by coincidence. If you look at this little blue line, it corresponds actually to price of the cars, because it correlates with the dealer you bought the car. So if it was a Mercedes dealer, right, you pay lots of money and things like that. And you can see here Mercedes-Benz, you know, so higher price, and you know, Kia again, you know, lower price. So this is very nice because you can sort of project everything in 2D, put some nice color plots and sell your ideas, write a nice thesis. And I remember this individual had done lots of plots like this, including actually lots of experimental results of crossing cars. And you know, it was like the impact of the force and crossing this with a steady wall, with a moving wall, had lots of variables, and it was trying to make physics out of these things, okay? The only thing I'm going to say, whatever you see here, it doesn't actually work in any real problem that I know. But people still do it because they think it's a valuable information, okay? So obviously I need to tell you a little bit how this method works. And just so that you don't get excited, the implementation of these algorithms is literally 1 line. Okay, so we will spend a whole lecture today about nothing. I mean, it's 1 line, right? Why bother? So we're going to make a lecture out of nothing. Okay. So let me, I will actually bypass this, okay? And bypass it. And bypass it. All right, so we're going to discuss first the non-probabilistic version of principal component analysis, and there are 2 interpretations that they come to be equivalent, okay? So some books use one and other books the other, but you need to know both because they are the same thing at the end of the day. So in interpretation 1, it says you do a projection basically of the data points from high dimensions to a low dimensional subspace to maximize the variance of the projected points. So you project, let's say you project everything on a line, right, in 1 dimension. You do it in a way that maximizes the variance of the projected points. I want you to remember this, okay? That's one of the approaches. And the other one is you do these projections to minimize the sum of squares of the projection errors. Okay? So pictorially, one is we said to maximize the variance of these points. These are the projections on 1-dimensional subspace. All right? So we want these points to be such that they maximize the variance. And the second interpretation is we want to minimize the square projection error, which is the sum of the squares of these blue lines. Okay? So what we need to do is we need to do the algebra and see what those things mean. And then if we manage to finish it, we need to see how we can go back and generalize this with a probabilistic version that I started the lecture today. right. A lot of things there. So let's try to be simple if we can. So these are our data sets, right? And I want you to remember, so n is the number of data points, and d is the dimensionality of the data. So each point is in d dimensions, okay? And we want to actually identify a low-dimensional representation of the data, and we call this dimensionality m, which is much less than d, okay? So we want basically to project the data in m dimensions, and for what you're going to see now, I'm going to fix n. Right, so I'm not going to ask the question, what is the lowest dimensional representation that I can have for this data set? Okay? Maybe as an outcome of the method, you may be able to put a criteria and see what that is, but right now we're going to fix M. We're going to assume that, so the space, this principal subspace has this basis functions, okay, ui, from I equal 1 to m, okay? We're going to do, remind ourselves what the sample mean looks like. All right, so this is the definition of the sample mean, remember? And this is the sample covariance. The only thing I want you to remember again is the data are in d dimensions. So this matrix is d by d, okay? Sample mean and sample covariance, and nothing going up. Okay, so the interpretation one is, we need to project in this principal subspace in a way that maximizes the variance of the projections in that subspace. So what I'm going to do is I'm going to try to do this by starting with projection first in one dimension and then in 2 dimensions, etc. So that we can see what's going on. So let's project the data first in 1 dimension that is spanned by this vector u1. So that's, I want to project high dimensional data in 1D, and this manifold, right, in 1D is spanned by the vector u1, and I'm assuming that is a unit vector. u1 transpose u1 equal to 1. Okay, would you agree that the projection of xn in the subspace with base u1 is u1 transpose xn? We agree? Right? I'm projecting in 1D. Would you agree that the projection of the mean is u1 transpose x bar? Would you agree with me that this is the variance of the projections? It's the sample variance, right? Sample variance, okay? So the sample variance is summation 1 over n of un transpose xn minus this, okay? And I am writing this in a trivial way like that. These are scalars, each of these. Actually, there are 2 vectors, but there's dot product, so I can pretend that they're vectors. So write this as u transpose. And move u1 transpose outside. Move, there is transpose, move u1 outside. When you take transpose, these things will reverse, right? And then inside, what is going to be left, you know what? It will be this nice sample covariance matrix. So effectively, the variance of the projected data on a subspace spanned by u1 is u1 transpose s u1. Nice result, all right? So the variance of projecting all the data in 1D in the direction of the vector u1 is u1 transpose s u1. And what's the idea we said of principal component analysis? One of the interpretations is project them in the subspace so that you maximize the variance of the projected point. So what we need to do is maximize this. And we're going to maximize it with respect to what? To what? U1, right? Because we don't know what that subspace is, what is, the appropriate subspace to maximize the variance. So we're going to say, find U1 to maximize this. And because U1 is a unit vector, we're basically going to solve this optimization problem. Right? So if you, obviously you're going to have to take derivatives with respect to U1, you're going to have to take derivatives with respect to lambda 1. And it comes out, I mean, you can immediately see, right, if you take derivatives with respect to U1, you basically get SU1 times lambda 1 U1. It comes that U1 actually is an eigenvector of the sample covariance matrix S. Okay? And because you remember the variance of the projected points is U1 transpose SU1, and we want to maximize this. So really, lambda 1 is the variance of the projected points, and we want to maximize that, which means which eigenvalue lambda 1 is going to be? Is going to be the biggest eigenvalue of the sample matrix of the covariance matrix S. You see that? Again, right? The variance of the projected points is U1 transpose SU1, all right? So obviously, because if you take here U1 transpose SU1, that's equal to lambda 1. If you want to maximize this, means you need to have the largest eigenvalue. So when I say this is the principal subspace, right? In this case, U1 is the eigenvector that corresponds to the largest eigenvalue, and lambda 1 is the largest eigenvalue. So U1 is called here the first principal component, okay? And soon we will see how the second principal component is going to be defined using recursion. So, but it's nice that somehow, you remember I told you the whole method is going to be one line? You can actually guess that that one line will be solving really an eigenvalue problem, okay? So now, suppose now you want to project the data not in 1 dimensions but in 2. What will you do? So you already know how to project in 1, all right? Now you want to project in 2. So what will you do? Recursively. We already computed how we project in 1. So we're now going to project in 2 in a subspace, right? That is spanned by U1 and U2, but we should make U2 to be what? Orthogonal to U1, right? So we don't waste our time. So U2 will be orthogonal to U1. So effectively, let's say you have done this problem up to dimensionality m, and you want to select um plus 1. So in our case, let's say this is U2. We're going to maximize the projected variance in U2, all right? But at the same time, we need to be sure U2 is a unit vector, and at the same time, we need to be sure that U2 is orthogonal to all the previous U's. In this case, let's say U1. So, not surprised, if you do the calculations, it comes out that actually, um plus 1 is the next eigenvector corresponding to the next eigenvalue in order of magnitude, effectively. Okay? So you can actually complete this recursively. So the contribution to the total variance basically by each of these components ui is lambda I divided by the summation of the lambda i's. This summation of all the lambda i's is the total variance. So basically, if you do this in a projection in an m-dimensional space, you will you will only capture a percentage of this variance, right? So from m plus 1 to d, you will not be capturing it. So you can actually use that, if you like, as a criterion. You say, how much variance do you want to preserve in your data? And based on that criterion, you can figure out what is the optimal dimensionality that you want to use for your data. Okay. So we are done actually with this interpretation of PCA where you project in a way that maximizes the variance of the projections. Okay, so we'll do now the second methodology, which actually will give us the same results, very different from what we have seen before, but also very instructive. And so we will see this methodology as the one that minimizes the projection error, if you like. Okay? So let's say that you have a basis in d dimensions. We call this ui. So you can actually project any vector exactly on these vectors ui, and the coefficients are nothing else but x transpose ui. You remember this from your early days, right? So if you have vector, you know, you can, I mean, you can project x in any basis, right? And the coefficients are basically x transpose times ui, because these vectors ui are orthonormal. So if you take an inner product of this thing with, you know, let's say uj, all right, everything on this side will be 0 except when you hit the component uj, so you're going to get basically an equation like that. Okay, so this is if you know, you represent x using all the vectors that form a basis in the d dimensions. But we want to actually do an approximation in a subspace that is m-dimensional. So this is how the approximation is going to look like, right? It is, on the first hand, it may look a little bit weird, okay? But when you see the plot and the final results, it will actually make a lot of sense. So let me express this first mathematically. So we are going to find an approximation of this in m dimensions. So what I'm going to do is I'm going to use an expansion like this, but the projection will be only in the first m vectors ui. All right? So I'm going to project on this m-dimensional space. You know, I still use the same basis, but I'm going to use the first m vectors. So you can see now why I call this m-dimensional, because if you don't account for this, right, you only need the m coefficients to describe what's going on, not d coefficients. Okay? And so that's an easy term. And then, for regardless what point xn you are referring to, so regardless of what the little value of n is, the remaining term is going to be involve this vector ui from m plus 1 to d, where these coefficients don't depend on n. Okay? So sort of this would be the error that you do in the approximation, and that error will not depend on n. Okay? We will see shortly exactly what this thing gives us when we try to compute these coefficients. But think again, this it's sort of an approximation, right? Plus some correction term, and this correction term does not depend on n, and it involves the vectors on the subspace that is orthogonal to the one that we do the projection. Right? So you can think if you're projecting on this plane, all right? So this is the vectors on this plane, and what this is basically a vector vertical to this plane. Okay? All right. So when you do this for, you know, the question is, what are these coefficients? What is that coefficient? And, you know, what should we use there? So let me, so we said that the second paradigm of PCA is to minimize the projection error. You remember? So the projection error is 1 over n summation over all the n's, and I'm going to use this square error of the exact point xn minus its approximation, and remember we said its approximation looks like this. So basically our criterion is find me the coefficients z, the coefficients b, and also the vectors u, so when I, you know, I represent this in m dimensions, this approximation minimizes the square error. Okay, and again, I think I gave you a picture somewhere, right? So the square error is basically this square plus this square plus this square plus this square, right? Where these are the approximations on the principal subspace, but when I write the general expression, we don't know exactly at what point. Here I take orthogonal projections, but we don't know that yet. Okay, so these points can be anywhere here, but we want these errors to be minimized. Okay, so we want to minimize that. You guys, by now, you realize everything in machine learning is an optimization problem. In this case, it's trivial. You take derivatives, you set them equal to 0 with respect to each argument. And here is what you get. You get that the coefficients z and j are nothing else but the projections of xn on uj. Not surprise, right? Not surprise. And then maybe, because if you've not seen this before, maybe this is a little bit new. It comes out that these coefficients that don't depend on n, they are nothing else but the projection to out of the subspace vectors u of the mean. Okay, that's why they're independent of n. So you take the mean of the points, all right, and you project it. And you remember this summation here is from n plus 1 to d. So these are all the vectors orthogonal to the subspace. So the bj's are x mean transpose uj from n plus 1 to d, where x again is the sample mean. So if, how do you get this? You set the derivative is equal to 0, and there is no algebra. The algebra is this equation. The algebra is the answer, okay? So if you plug in now this with these values in this expression, and you compute the error, this is xn is the point in high dimensions, this is the approximation in m dimensions. I'm going to go directly on the final results, all right? And the final result looks like this, okay? So you notice basically the error that you do, so let's say you project on this plane, what are you missing? You know what you are missing is what is vertical to that subspace, and you can see here it involves this vector ui's from n plus 1 to, to d, okay? And the coefficients, again, this is interesting, look like a projection, but they are projections of xn minus x mean, okay? So remember, for writing the error, it comes out from the algebra that these projections are xn minus x bar on each of the vectors ui. Okay, so this is, again, you could have guessed this thing because if you try to minimize the errors, you have to take orthogonal projections, okay? And, all right. So, now, I haven't really shown you yet that the use, obviously, better come to be the eigenvectors of the sample covariance matrix, all right? The way to see it is very simple. So we said that this is the approximation equation, this is our error, okay? And you remember our objective is to do what? Our objective was to minimize this error. So take this and plug it in inside the summation, and then what you get is summation of 1 over n over the data points over the dimensions beyond the subspace dimensions from n plus 1 to d of this square, and it comes out that this gives you ui transposes ui. All right? And you want to minimize this. So can you tell me these vectors ui from n plus 1 to d, are those the eigenvectors corresponding to the largest eigenvalues or to the smallest eigenvalues? Before, remember, we maximize the variance. Now we have to minimize the square distances from n plus 1 to d. So the vectors ui from n plus 1 to d correspond, if we want to minimize this, right, and you do the minimization problem the same way we did before, what eigenvalues and eigenvectors are you going to get? The smallest ones. All right? Okay, so we are basically, so again, if let's say you have a problem in 2 dimensions, and you decide only to do projections in one line, in 1 dimension, then the eigenvector u1 is going to be the one corresponding to the largest eigenvalue, all right? And the vector corresponding to the orthogonal subspace will correspond to lambda 2, and the minimum value that you will get here will be equal to lambda 2. So the distortion measure, it's basically what you see here. It's summation of the eigenvalues from n plus 1 to d, okay? So one way or another, the 2 interpretations give the same results. They're fundamentally completely different way of thinking or deriving them. So they seem to have different physical meaning, but they're identical. And they were reported separately in the literature, so you can, you need to think basically of both of them. All right, Now, I need to show you some practical things to convince you what this means, right? You know, how are you going to use it in one-line program to actually do some model reduction, data compression. So let's go back to the equations that we had. I am not going to do the derivation, right? Because it's a substitution of these equations we had on the previous slide. But let me just say that, the following. Every data point, all right, every data point, what I can do is I can write it as the mean value of all, this is the sample mean, plus, all right, these projections on the m eigenvectors ui, okay? So here again, the coefficient is basically xn minus x mean transpose times ui. So effectively, you can appreciate, originally, you started with vectors in d dimensions, but with this equation, when you look at them to describe now this point, you only need m coefficients. So now you have approximated in m dimensions, not d dimensions. So if this is 10,000 and m is 3, the savings are enormous, right? Because you are doing calculations in 3 dimensions rather than 1,000 dimensions. So obviously that's, we use this in data compression. So so before I give you actually a few examples with images on how this data compression works in practice, let me give you still another methodology that comes out to be equivalent to PCA with a different name. Okay? You remember this scenario where the same thing was stolen by different communities, given different names, but it's the same thing at the end of the day. Okay? And this goes under the name of singular value decomposition. And any of you that has taken a course in numerical linear algebra, I am sure you spend time discussing that. Okay? We don't have such a course at Notre Dame, unfortunately. So let me tell you what the singular value decomposition is. In the methodologies for PCA, what we did is we started with a sample variance, and then effectively we solved an eigenvalue problem, right? So what I want to do is, let's start directly with the data matrix X. So this matrix X, every row is one data point, and remember every point is in dimensions D. Okay? So this matrix X, this is what we call the design matrix, is n by D. Right? N, the number of points, D, the dimensions. So what you can show, and this is a generic thing, going with the name singular value decomposition, you can write this matrix X as an orthogonal matrix U times this diagonal matrix S, and we will discuss it in more details, plus another orthogonal matrix V. So X equal U times S times V transpose. And I have highlighted in this case exactly what parts of U and S are non-zero. So this part here, so I split so the U is of dimensions n by n. All right? Remember, this is n by D, so this is n by n. All right? This is n by D, and this is D by D, so the result is n by D. Okay? So this part here is 0. This part here, it has in the diagonal sigma 1, sigma D, and we will see what is the meaning of those. These are in linear algebra are called the singular values. All right, so we will see if they are related to the eigenvalues we have seen. This part here is 0. Okay. Remember, n is in practice is way bigger than D, right? So you can think, you know, this is, I don't know, in 20 dimensions, but you have 10,000 points. It can be actually the other way around, and I'm going to do an example of that as well. But here, n is very big, and this is a little bit smaller. So this part here is 0, this part is 0. And so U is an orthogonal matrix. S has these singular values in the diagonal, but below that has zeros. And V is another rotation matrix. So a few facts. if you accept this decomposition that is correct and you can do it, okay, for this data matrix X, one line of programming, you can actually do the following. If you form X transpose X and you substitute this as X, right, and you use the fact that U and V transpose are rotations, are orthogonal matrices. You remember, if you have an orthogonal matrix, U transpose U is equal to identity by definition. Okay? So you can actually, if you form X transpose X, you get in one line this amazing result. X transpose X times V equal VD. And you know what that means? That this matrix V has columns which are the eigenvectors of X transpose X. And D are, because D is diagonal, is basically the eigenvalues of this matrix. And similarly, if you form XX transpose, it comes out that U, the columns of U are the eigenvectors of XX transpose, and again, D are the eigenvalues. Okay? And in literature, you call them right and left, eigenvectors, So V are the eigenvectors of X transpose X, U are the eigenvectors of XX transpose, so this has a lot of details. Basically, these things don't come accidentally like that. So here is the idea of making this to look like PCA, right? Using the data, the design data matrix X, not using the sample covariance. Here's the idea. So let me go back on this. Here, you remember we said my data is n by d. Suppose now you say, you know what? If these singular values, we order them here, by the way, in order of magnitude. If they start becoming smaller and smaller and smaller, maybe instead of using all d of them, how about if I use only m of them and forget the rest? So effectively, if you do that, this matrix becomes not n by d, but becomes n by m. This becomes m by m, and this becomes d by m. And effectively, this truncated singular value decomposition requires, significant reduction in the number of parameters. Okay, and I'm not going to go in the algebra, but you can actually figure out, the number of variables that you need here is n times m plus m diagonal plus d times m. But effectively, this is sort of a truncated version of singular value decomposition. So what is the idea of using singular value decomposition? Do an SVD directly on the data matrix X, decide to truncate this at order m, and then effectively all your points X are approximated in m-dimensional space. Okay, and it comes out that's equivalent actually to doing PCA, but the origin again is a little bit different. The implementation looks slightly different, and here is a few results. And again, when you look at these pictures, you don't have a sense of these algorithms unless you look at the program and you say, let me do this. This is, this guy Bozo bothers me since I was 2 years old. So let me see how he looks like, all right? So the original images are 200 by 320. And so you do singular value decomposition. So, you take basically this data, right? And you write them as this design matrix X. And then, you truncate this SVD, keeping 2 singular values, 5 singular values, and 20. So if you truncate using only 2 singular values, you don't get anything. I don't see any bozo. 5, you can see something with some imagination. 20, you can see something. And 200, actually, you capture a lot. Okay. Let me see if there's any other example. Well, you can do this basically for the images that I gave you. So this is actually the data set, okay? And this is, this is the eigenvalues corresponding to the principal eigenvectors, All right, so if you do PCA, this is lambda 1, lambda 2, lambda 3, lambda 4. This is the mean value. And these are the corresponding eigenvectors. So I mean, if all your data look like 3, right, it's not surprising that the eigenvectors look some versions of 3, okay? But look what happened. I think if you actually, so you notice from here, these values of lambda 1, okay, they're all significant. But if you plot lots of them, all right, like 800, you notice if you compute the distortion measure from n plus 1 to d of the summation of the lambda i's, this distortion measure actually goes, it starts basically stabilizing, okay? All right, so depending how many values you keep, all right, if you keep 800, the distortion basically, it has reached practically 0. You capture all the variance in the data. So you can decide and say, you know what, this keeps so much of the variance, so I'm happy, and that's where I'm going to stop. And so you can see here reproduction of the approximation of the digits 3. So let's say if this is your original digit 3, this is the dimension, the reconstruction of this from one-dimensional subspace. That's not bad. You take an image in high dimensions, right? You project it literally in vector u1, and you get this. If you project it in 10 dimensions, you can actually see it now, it's turning a little bit. If you project it in 250, you actually get something much closer. But depending on what you are interested, right? I mean, everybody can see that this is 3, and you say, that's nice, in one dimension, okay? So it works. And, there's a lot of different examples with faces, and, you can see reconstruction here using 5 faces, 10 basis functions, 400 basis functions, etc. And again, in this plot, it shows the mean square error, all right? Basically the same sort of criterion as what we had before. That's the reconstruction error. All right, 122. So let me see what I can tell you on a little bit of time that we have left. So okay, so I mentioned that in what we did before, right? Let me just go to slide 55. All right. So in what we did before, we assume that we have a lot of data, and n is way bigger than the dimensionality d. So now let's assume the following, that the data are in very high dimensions, and we have very small n. I mean, that can be a real problem, right? So you have a few data, but in very high dimensions. So how do you do PCA actually when you have very few data and they live in high dimensions? So there are lots of tricks, by the way. That's why these methods are so powerful and they're being used everywhere. So I'm going to tell you one of the tricks, okay? So if you form basically the covariance matrix in this case, right? The covariance matrix, the sample covariance matrix has dimensionality d by d. So if d is very large and you go and you say solve an eigenvalue problem, try it with MATLAB. Try to solve an eigenvalue problem in 500 dimensions in your PC and let me know. You will have a hard time, okay? Actually, I doubt you will be able to do it, okay? If you ask for the first 3 eigenvalues, no problem, but ask for all 500, you won't be able to do it, and if it is 10,000. So this is d by d, this is not good, right? This is what we did up to now. So here is the magic of tricks, right? If you know your algebra, you can imagine a lot of tricks. So the eigenvalue problem that we have to solve, which is what we did with PCA, is basically this sample covariance matrix, 1 over n x transpose x, ui equal lambda I ui. We agree? That's our eigenvalue problem. Here before we had s ui equal lambda I ui. So what I'm going to do is, as part of the trick here, I'm going to multiply the left and the right side with x. So I'm going to multiply x transpose x ui. So I'm going to put an x here, and I'm going to combine those things together inside parentheses so they can inspire me. And when you look at this equation, what can you say about xui? That is now the eigenvector of xx transpose. What's the dimensionality of xx transpose now? Remember, this is d by d, this matrix, x transpose x. What's the dimensionality of xx transpose? N by n, and n is small. So now the eigenvalue problem that we have to solve to compute xui is a very inexpensive eigenvalue problem. Okay? So here is the idea. Call this vi and solve the eigenvalue problem not for the covariance matrix but for xx transpose. Right? So you solve the eigenvalue problem for xx transpose. Okay? Now usually the data are centralized. Okay? So when you write the design matrix, it's typical you remove the mean, which means basically that you will only compute up to n-1 eigenvalues. Okay? So you will account basically for the fact that you've removed the mean out. So xx transpose here has rank n-1. Okay? But bottom line is the computational cost for the eigenvalue problem goes from d to the cube to n to the cube, and n is way smaller than d. So if you compute then this eigenvectors v, you can go and you normalize them. You can actually solve from the equation that we started that the actual eigenvectors of interest are given by this nice equation. You just have to multiply. Bottom line, solve a modified eigenvalue problem using xx transpose, compute the v's, compute the lambdas, and once you compute the v's and the lambdas, the u's are given by this nice expression, and then you are able to address problems in high dimensions with very few data. Okay? So depending what you want to do, there are lots of tricks. Now, there are way more tricks that have come the last 10, 15 years, and I'm not going to be able to tell too much, but if you have if you have data that come from simulations, there is the method of snapshots, and lots of people make careers actually out of these techniques and had a good life for many, many years. But lots of these problems are done now. Okay, so you need to know them, and now you have to move forward to these generative models and think a little bit better than these techniques. And actually, if you think better than these techniques, I can tell you, whatever you do for your research, there's absolutely no way you can publish anything until you actually compare with these techniques as well. Nobody will accept you because these techniques, they always work. The question is your method working better for non-linearities and some weird data? But if you get something that doesn't look better than this, you are in trouble. So you need to know these techniques. Okay. All right, so let me go back and we can finish on a Thanksgiving, pre-Thanksgiving lecture. We finish on this probabilistic version that I started. So we basically are going to try to introduce some probabilistic ideas here. And in particular, we're going to try to make the interpretation of PCA to be that of a generative model. Okay, and so we will see at the end of the day how this relates with the standard techniques. I mean, generally speaking, right, the concept that you have to solve an eigenvalue problem is not good. Anytime you have to solve an eigenvalue problem, you should be concerned. There are thousands of problems that there's nothing you can do. There is an eigenvalue problem, but it's not good. All right, so let's see what these probabilistic interpretations are doing. I mean, actually, it's beyond the eigenvalue problems, right? When you project something from low dimensions to high dimensions, there's already lots of information where you're in low dimensions and you go to high dimensions. How can you say from Z you go to X and you give a number? You need to be able to say, plus this error because I lost information. The PCA methods don't do that, right? You need to be able to be probabilistic. So we are going to start with some latent variables z, and I'm going to take the simplest possible model looking like that. And then for each value of z, with a linear model, we're going to generate x through this generative model, again a Gaussian isotropic noise, and we have a linear model, wz plus mu, and w again will be of dimensions. If this is dimensionality d, and this is dimensionality m, so this will be d times m. Okay, so w will be d times m. It's not a square matrix. We have no idea what w is. We have no idea what sigma squared is. But somehow, if we can compute those, there is hope that this model will make sense. Okay. So if you like this without the probabilities built in, basically this is what is called a linear latent variable model. Okay, so x equal wz plus the mean plus some Gaussian noise. This is extremely powerful. It comes up everywhere, right? We already have used it actually here and there in a completely different context, but the idea that somehow you would take high dimensional data and approximate them with something in low dimensions in this form, and then still account for the fact that this model is wrong by putting some noise, that's very powerful, okay? And it doesn't really matter what noise you put, because I can make every model that you throw at me to look like this. I can change the variable names, etc. So this is, if you understand this, anything else, basically, you can make it to look like this. So just a reminder of the equations. We sample on this prior model, if you like, in latent space. And then here we go in 2 dimensions. If we knew what w is, right, in this case would be a vector. So effectively what we generate x's, okay? And because of the isotropic noise, the x's would be somewhere on this line, with this Gaussian noise. And if you integrate z out, so if you multiply this, multiply with that, and then you integrate z out, you get a marginal of p of x, so this is the likelihood model, that the covariance looks w transpose plus sigma square I. This is very important to remember because this sort of equation comes in everywhere. Okay, we will see this even when we do Gaussian process next semester. This is sort of a standard thing that comes in front of you. Okay, so there's no algebra involved, just linear Gaussian model, so you get here something that looks w transpose plus sigma squared I. Before I move on, right, and tell you how we're going to compute w and mu and things like that, let me just say the following thing. If p of x is going to be Gaussian, all right, and we know this from this model, p of x is Gaussian, the whole idea of doing this latent variable representation will be to use less parameters than the ones that we need to describe a multivariate Gaussian with an isotropic covariance. If you're going to do latent variable representation, and at the end of the day you will need the same parameters as to describe mu plus a generic covariance, then you are ruined. The idea is, can you actually do this and having way less variables than the ones that you need to describe a multivariate Gaussian. And remember, the covariance in a Gaussian, right, symmetric. So you really have d times d plus 1 over 2 components plus d for the mean, all right? So we need to be way less than that. So w has to be such that the number of parameters in w, when we sum them up, basically will be less than the variables that we need to describe in a Gaussian. All right. So this is the proof of that equation. I don't need to go through this, okay? This is a generalization, okay? So I'm going to bypass this. Let me, because I did not bother to tell you anything about this, right? But maybe you could have guessed it. Something that I did not say anything and it is a pathology of all of these maps we discussed today, is that if you take this subspace where you do the approximations, where you project the data, and you rotate that subspace with some rotation r, the answers don't change. So for example, we did our model, right? And we defined everything in terms of W. So let me, if instead of W, I use W times a rotation, let's see what's going to happen. If you use W times a rotation, all right, if instead of W, you put W times a rotation, and you form W transpose, because this is what comes in the likelihood, and at the end of the day, the calculation of the W will be by maximizing the likelihood. You can see R transpose is identity, so you get the same answer. So you can rotate the whole subspace, nothing changes. Which means when you do optimization, you better be sure, do you actually get some random rotations, or are you integrating the rotations out? What do you do? I mean, how are you going to be comparing, implementation of this between two groups if one comes with one rotation, other with another rotation? So in the notes, you will see some discussion on this issue, right? It's not trivial, okay? I mean, somebody can say, I'm going to fix the rotation, right? Another way actually to address this is to get rid of this issue with the rotation is to take that the components, that the columns of W are actually orthogonal. And if actually you do that, then you get the same identical results as the PCA we discussed before. Okay? There are many other fancy ways of accounting for the rotation R. Just remember when you do this, if you throw a rotation, you will get basically the same answer. So there is an issue of identifying what is the proper W in your problem. All right, so this is the likelihood, all right? And as we said, we're going to maximize basically to compute W and sigma squared by maximizing the likelihood. And if you take the log likelihood or you expand the Gaussian, right, you're going to have to actually invert this nice matrix, the covariance matrix. You remember the Gaussian? In the exponent, there's an inversion there of the covariance. So you're going to need to take the inverse of this. And the inverse of that, thanks to the matrix inversion lemma that I told you, you will see it a few thousand times. There is a very nice inversion formula, okay? And the cost of this nice inversion formula, it's actually, you're only inverting an M by M matrix, okay? Not D by D, okay? So if somehow you don't know about your matrix inversion lemma, you're going to be inverting something in 10,000 dimensions when you can do the inversion in 2 dimensions, okay? So matrix inversion lemma, okay? For those who forgot, this goes also under the name of Woodbury identity. It looks like that, so I gave you different scenarios on how A is here diagonal, B is a long matrix like that, this C is a long matrix horizontally, and if you fit the parameters, then you get a nice formula for this. All right. So we're going to use, we're going to take the log likelihood. All right. So the log likelihood is going to involve this matrix C. All right. So I just put this to get a compact notation, and we're going to set derivatives with respect to mu and W equal to 0. So when you maximize this, the mu comes to be, no surprise, the sample mean. We could have guessed it again. And here's what the answer comes for W. Okay, I'm just going to give you the answer without much discussion here. So you can show that U is an orthogonal matrix. Okay, LM is a diagonal matrix, and R is a rotation. Let me see if there is. So UM is a matrix of magnitude D times M, And at the end of the day, its columns are given by the subset of the eigenvectors of the data covariance matrix S. So not surprising, right, that somehow the m principal eigenvectors of the sample covariance come to define that U. Lm is an m by m diagonal matrix that consists of the m largest eigenvalues of the sample covariance matrix. And R is an arbitrary rotation because I told you you can only compute W up to a rotation. Okay? So effectively, it seems that PCA is there. The only difference is that it's not probabilistic, right? I mean, we computed W, but effectively, we have a probabilistic model, all right? We have a probabilistic model, and more importantly, what is my equation? All right? More importantly, we have a model basically that takes us from this latent representation Z to the high dimensions X, okay? We know W, we can actually go from low dimensions to high dimensions, and probabilistically we introduce noise and all these nice things. You can do the opposite. If you want to think of this problem as a model reduction problem, you can actually use the Bayes rule and go from high dimensions to low dimensions. And I saw the answer somewhere, right? Here's the answers. So if you want to go from high dimensions to low dimensions, it's also Gaussian. This is the mean, all right? And this is basically the covariance that you get. So actually, when you take a point in high dimensions and you project it in low dimensions, you don't get 1 point. You get a distribution, all right? So lots of times, for plotting reasons, you actually don't care about this, and you will go and plot the mean only. You say, that's the mean projection, okay? But the nice thing here is it allows you to actually have some noise. Okay, and then there was this noise in the model, and when you do the optimization model, you maximize the likelihood of the data with respect to sigma square. Again, by a miracle, it comes out that the MLE solution for sigma square is given by 1 over d minus m, and remember, d is the total number of eigenvalues, d minus m is the eigenvalues that you disregard, right? And so it's basically the average of the disregarded eigenvalues in your problem. So it's sort of, and if you think the eigenvalues being the variance basically in each of these directions, is basically the variance that you're losing when you project in m dimensions. Okay? So this is, again, very straightforward result, and there is sort of some little tricks in the calculation, and the original paper that's actually very fantastic read. You know, I believe in one of the links in the slides you can actually go and look at this. So I actually sort of, there is a discussion in the slides, you know, about all of these things with the variance, so you can read it. There's really nothing nothing specific. Okay, so. So let me actually finish, because we spent much time talking about expectation maximization. You can do the MLE estimate for this problem using expectation maximization. And you know how it is? If I can find it rapidly, you know what you need to do is, you remember what's in expectation maximization? You have to form the joint log likelihood, and then take the expectation of this with respect to the posterior of z. But the posterior of z, we just derive it. I gave you the probability of z given x. So you have a whole algorithm where effectively the first thing is you approximate the posterior of z, you compute the average, the expected joint log likelihood, and then you take derivatives of this with respect to mu w at sigma squared. Then you update the thing, and there is sort of nice examples in the notes to see expectation maximization on this problem working extremely nicely, and the formulas look complicated. And out of respect for me typing those things, please read them, because that is a very nice application of EM for this sort of problem. We will do way more on model reduction and introduce nonlinear models and generative ideas next spring for anybody who's interested. But for now, I think I'm going to abandon you with this. And when we come back next Tuesday, I'm going to do a review of the whole class. And that will be our last lecture. Enjoy your Thanksgiving, all right? So I'll see you in 2 weeks. It's like Bayesian models for model reduction.
I think Bayesian surrogate modeling or something?
Yeah, surrogate modeling, yeah. It's
Just
really a machine learning 2 course, okay? And
just search for Professor